I think we should start with it being us. Big us? Big us! Yay! Now, how do we see
Mr. Duck.
who's coming?
Right there.
Great. Banter, banter, banter.
Got all our parts. Books, things. Good.
Mm-hmm.
We've got a dog.
You're just checking to see if we can be seen.
Yeah.
And there we are.
Oh.
Okay. Okay.
Oh, stop. Nice.
Great. It originally showed 2 people here, or now it's showing 1.
One was me.
One was you. Okay. And the other one is probably this. So, well, why don't we go ahead and get started?
Yeah.
So this is the heartbeat monitor circuit, and it's been really awesome to see how popular this circuit is. We've gotten a lot of comments across TikTok, YouTube, and Instagram being like, show us how you make this thing. And we kind of did. I think most people wanted to actually give it as a Valentine's Day gift. So we might be doing this a little late, but better late than never. We did release a short on it,
Right.
but this is like the deep dive.
Yeah, the short was like 30 seconds. So here we can take the time to actually break it down and say what each part does and why it does what it does.
Where did the heartbeat circuit come from? Like, is it a popular circuit for you as a professor? Like, it's part of your class, right?
Yeah, so I teach an introduction to circuits for biomedical engineers. It's a college junior level class, and the students, it's very interesting teaching biomedical engineers because there's so much to learn as a biomedical engineer that you never get to do a lot of the engineering because you're always in an introduction class. So I tried to make the electronics class very biomedical centric. So the first couple weeks are resistors and capacitors and the basics, but very quickly I try to get into like, let's build something that is biomedical related. And this was the first lab that I invented for this class that was like, oh my God, there's biomedical things in it. And it fell out of a different experiment where it was in the mechanical engineering class. We were like looking for stuff. We always want interesting sensors. And from the light sensor, we saw that, oh, if you like push your finger hard enough into it, you could see your heartbeat. Isn't that fun? So it just kind of fell out of that of like, well, what if I take this circuit a little bit further and a little bit further? And after a while, I was like, wait a minute, this is a thing. This is like in your smartwatch.
This is in your smartwatch, exactly.
But the smartwatch cheats. They've got a circuit that was built at the chip level that does it. So they don't have to do everything from scratch like we're about to do. But this is how they started it.
Exactly.
This is how they created it. And so we're going to go through the same process so that you could see what choices the designers made and what you can change. Because I think everyone's skin is a little different and everyone's heart rate is a little bit different and the noise environment you're in is a little bit different. So it's actually interesting to go through the process of building the circuit and seeing why those decisions have been made.
Yeah, awesome. We've got people.
Nice.
Yeah, and they're like, did they see the chat? And they're like, no, I don't think so. Guys, we can see you.
Oh yeah.
We see you. Ask us any and all questions. We're just going to be building it, but like ask us anything about being entrepreneurs, being engineers, job opportunities out there, what the landscape is like. Not that we can give you a job, but yeah. Those are our most popular comments.
Yeah.
This person logged in. Oh, they're on a mission. I want to see the circuit diagram in all caps.
Good.
You're going to get it. Yes. So why don't we go ahead and dive in and not tease these poor people anymore?
Well, you had the great idea of treating this like a cooking show. And just like a cooking show, we would start at the end to show you what we're about to make. And then we'll dive back to the beginning.
Someone clocked my t-shirt. Calculon. Hell yeah. I need to make my fiance a similar project. I'm dying to see this. Heck yes.
Great. Okay, should we jump to the zoom in?
So we can take a peek? which is something I can do.
Yeah.
Hold on. There we go. Now we're little. Okay, how do I get back?
And then go to desktop. So we're using OBS, Open Broadcast Studio, to flip back and forth between our fancy camera
Oh no,
system.
I lost it. Okay.
Right. Go to desktop, and then you can have the app as well.
Okay, just do it. I don't know what's going on.
Oh, sorry, that's called desktop.
Yeah, okay.
That was confusing. Okay, so what we can see on the right side of your screen is the circuit.
So we're showing the final product first. Don't freak out, guys.
Yeah.
We're not just gonna like, show this and be like, we did it. Like, we're just showing you what it's gonna look like at the end.
And on the left of the screen is the NLab app that's reading the voltage that comes from actually one of the intermediate points within this circuit. And that's the part that's going to show us our heartbeat when we touch the sensing part.
So there's my little heartbeat. But it's going to look a little different from you because this is a heartbeat circuit that's built for you, custom for you.
Right. Yeah. As we go through the design process, you'll see there's some like decisions to make. And when I was making those decisions, I was doing it based on what my heartbeat looked like.
Exactly. So you can pick and choose resistors according to like your skin thickness and stuff like that, right?
Yeah, I don't know how much of it's related to that as opposed to vibrations, but we'll talk about that as we
like
get
how
there.
much I'm moving my finger versus yours.
So you can see as I'm talking, my signal is rather erratic, and that's because my body is moving. But if I were to stay still,
looks like you're doing a job interview right now or something. Your heart's like,
and so that yellow line represents the heartbeat. In addition to that, I took that voltage from the yellow line and I'm applying it to this red-green LED up here. And so when my heart beats, it's flickering back and forth between green and red. It's kind of like stays on green longer than red. And the red represents when my heart is beating, and I guess green is not beating. And if we were proper biomedical engineers, we would call that the systolic and the diastolic heart phase. Those all have names.
I didn't even know that had a name. That's interesting.
Right. Those are probably the names you use with the blood pressure monitor. But anyway.
Okay, let's get into it.
Okay. So this is where we're going. And I'm going to take the NLab out of this breadboard. And
we got a question. Is NLab, while you get set up, is NLab an oscillator? It is in that it's a function generator. It can send an oscillating
it's
signal.
It's an oscilloscope.
Yeah.
Which sounds a lot like the word oscillator, but it's actually kind of the opposite of an oscillator. An oscillator would be the thing that makes a signal.
But it does make a signal.
Well, but the main purpose of the NLab is to read the signal.
Yeah.
So that would be an oscilloscope. But it's also a function generator. Mm-hmm. That's the device that makes things. But a lot of times you can't see what it makes. So usually the first thing you do is the thing that makes the voltage, you plug back into itself so you can see it. So on the NLab, you jump right across here. So here, when I touch it, you can see it like it's seeing me touching it.
Yeah.
And then it's also power supply. So the NLab is the three things we need to build the circuit. It's the power, it's the ability to see the signal, and that's all we need for this project. But some other projects would need the function generator as well.
We should just have the three machines on standby for when, when people are like, what is the
Unfortunately, they're really expensive, so we actually don't have them all.
Case in point. Yeah. Okay, so now we start with the block diagram, right? And we move into the circuit diagram.
Yeah, so the first thing we want to do is kind of describe what we expect.
This is good engineering practice. So
I'm going to draw this as a graph. I'm going to call it voltage versus time. And so what I
kind of write time there.
Time.
Good job.
The voltage.
Good.
And so what I expect is kind of a flat voltage. And every time my heart beats, I want to see like a lump. And as we already saw, because we cheated and we jumped ahead, was that the lump actually went down instead of up. We could change that with the circuit if we want. But this kind of represents heartbeat, heartbeat, heartbeat.
Mm-hmm.
And the way we're going to sense this is using light. So we're going to shine light into our finger. And then the light that bounces off of our finger is going to change color every time our heart beats.
That's right.
So when your heart beats, it pushes different colors of blood because the blood still has oxygen in it. And so maybe don't think of it as color, but like the change in reflectance changes. But anyway, the light sensor will pick up the change every time your heart beats. And ideally it would just be that.
Great.
So we're going to take a light. You're practicing drawing bigger today so that this is easier to read. The light is going to come out of an LED and it's going to hit my finger. And then it's going to bounce off my finger and it's going to hit a sensor.
The sensor is going to see the light bouncing off the finger.
Right. And ideally, it looks like that.
Great.
Of course, it's not going to be that easy, but that's what we kind of hope for initially.
Mm-hmm.
So I've got, this is from our NLab kit bag, a bunch of LEDs and light sensors. So the LEDs make the light, and then the sensor is going to pick up that light. We can kind of just paw through. We've got some blue LEDs and red LEDs and things like that. So what we want is a really bright red LED, and that's going to be this one. This is what we call a super bright red LED. It's bigger than a normal LED. So here's maybe a normal LED size, this little blue guy. So it's 5 millimeters instead of 3 millimeters. And the lens is clear because it's like a really high quality red light. This red light is red because the plastic is red.
Mm-hmm.
It's not as like nice as this one. So this is like a flashlight quality red LED.
Super bright, might blind you on the camera screen. Can we pause for a second? We have a couple of questions.
Oh yeah.
What if you accidentally bend the NLab pins? They're pretty hardy.
They are pretty hardy. This would be like stepping on a, you know, when you step on a Lego, it really hurts. This would be like infinitely worse than that. They're like pins, and they would get.
We really know how to sell our product.
I've stepped on it enough.
They're just asking like if we accidentally bend it.
Yeah,
like,
but you could bend them back. So here's the bottom of the NLab, and there are pins. You can kind of see those gold pins here. That's how it plugs into the breadboard. And these are a little bendable, but they're not really meant to be bent.
They weren't asking what happens if I bend it with my foot.
Yeah, but yeah, you could bend them with your finger. It would probably be easier to bend them with pliers, honestly.
Okay, and then the sensor emitting light is an IR LED. I think we answered this.
In this case, we're using red light.
Yeah.
In your smartwatch, they're probably actually using 2 different colors of LED. In fact, my Fitbit uses a green LED, and then it uses infrared as well. And by comparing the color light and the infrared light, you can also figure out your blood oxygenation level. In this case, we're not going to do that, and we're using red because it's kind of easy to see and convenient. I think there's other colors that would work too.
Great. Black LED?
Okay, there is somebody noticed the black LED. This is actually a infrared photodiode, which you might have seen before. This is maybe, I don't know where you see this now. This would be like the receiver for your TV remote control. Although most TV remote controls are radio now. But back in the day, you would see these guys. And then this guy is our infrared LED, which for some reason is like a square.
I'm going to let you answer this question, and then I'm going to put our dog away because he's making a lot of noise.
He's eating the floor right now. I don't know if anyone else can hear that.
He's 8 months old. I will have him make a brief appearance.
He's got carpet hanging out of his mouth.
This is our dog, Gimli, named after the Lord of the Rings character. Oh my God.
Bad.
Okay. They're waiting for the education. Go, go, go.
Floor. Yummy. Good job, dog. Okay, so that's the photodiode. That's an infrared photodiode. In this case, I want a red sensitive light sensor because the LED is outputting red light. So we want something that's most sensitive to red. And that is going to be this guy here. So it looks a lot like the IR photodiode in size, but it's got a clear lens instead of a black lens. And it's a phototransistor instead of a photodiode. And so there's 3 different types of light sensors, photoresistor, phototransistor, and photodiode. In this case, we're going to use the phototransistor. We've got other videos and content on like how to choose the different light sensor for the thing that you're doing. But I found that the phototransistor is a nice big response that is the right solution, and that's what your watch uses as well. So we're going to use that guy, and we're going to put all the rest of these LEDs away for now. And the first thing to notice on these guys is they kind of look identical. One is the big brother of the other, in that it's physically bigger than the other, and they have a long side and a short side. And 99% of the time, when you see something with a long side and a short side, that implies that the long side is the more positive side. So when we build it into the circuit, it's directional. We have to make sure it plugs in the right way. And of course, just to be annoying, the phototransistor is that 1%, where its short side is the positive side.
I still don't get it.
Yeah, and it's kind of manufacturer dependent in this case. So this particular manufacturer, which makes the nicest phototransistors, made it backwards.
Okay, so now let's draw the circuit diagram.
Yeah, so we're gonna switch to a different piece of paper so we can keep our block diagram separate from our circuit diagram. And so the first thing we're gonna do is we're gonna just turn on that bright red LED. So from 5 volts, I'm going to go to that super bright red LED, and light will come out. But if we just hook that to ground, the LED would burn out. We have to put a resistor in series with the LED to limit the current. And that will set how bright it is.
Yep.
And I believe I used a 1000 ohm resistor in that earlier circuit, but we could play around with that if you guys want to see the difference. When you make a smaller resistor, this will be brighter, and a bigger resistor will be dimmer.
And if you guys don't know what these symbols mean, like basically this is the light and this is the resistor that's needed to make sure that the light doesn't burn out.
Right.
Come to our beginner build session tomorrow, same time. We'll be walking through all that stuff. Anyway, continue.
And so this is the long side of the LED because it's the positive side, and this is the short side of the LED. It's the negative side, just for reference.
Great.
All right, now we need to find a 1000 ohm resistor. So I'm going to get out my baggie of resistors. This is how we've been packaging our resistors for a while now. We're trying to find a better way.
You see me shaking my head.
The resistors have color-coded bands on them. And so I'm looking for the 1000 ohm resistor, which is brown, black, red, gold.
Oh, we have an important question. Is it possible for you to make the circuit diagram as a whole thing and not separate? It's somewhat confusing that way. This is all going to be connected. Right?
I will draw one big one as we go, and we'll flip back and forth between the block diagram.
We're doing this piece by piece, but it's going to be a whole thing at the end. Is that okay? Wizzo, Job, Lab.
And I have a reason for that. The reason is that this particular circuit, depending on the room environment that we're in, we might need to change how we filter the signal. So I have a brand new light in our studio, and I didn't know if it was flickering at a specific frequency. So I didn't want to just be like, draw the whole circuit diagram and find out, oh, that light is smothering us in a specific frequency of light. So we're going to kind of see what happens as we go.
Cool.
Okay, so
keep going.
Why don't we build this first? So we need the long side of the LED to the 1000 ohm resistor to ground. And then our NLab has put ground and 5 volts on the right side rails of the breadboard and -5 and ground on the left side. So we need a wire to get from +5 to the LED. And of course, we like to make our own wires rather than use pre-made wires, because then they can be color-coded and they can be made to the exact right size. So I'm just cutting and stripping this wire. And the power supply is already on. So as soon as I plug this guy in, it should output red light. And it's nice and bright. And it has a lens on it that most of the light is coming out of the tip. So from the side, it kind of looks a little pink. And that's because all the light, like a spotlight, is coming right out the side. And the idea is when I touch it, it lights up my finger with red light. And now if I were to look at that very carefully, my finger is blinking every time my heart beats.
Yep.
Now, another thing that's going to happen, though, is it's very sensitive to motion. And so if I leave the LED hanging out of the board like an inch like this, and I put my finger on it, I'll be able to wiggle. And that wiggle will be able to pick up its vibration. It looks identical to the heartbeat. So I'm going to cut this guy down so that it's shorter and it fits in the breadboard more snugly so that it can't vibrate like that. So now I've cut it down really short, and it's going to go flush with the breadboard. But it's still functioning the exact same way. And if I was going to take a lot of time to do this, I'd also cut down the resistor. Just for time's sake, we're going to skip doing that. But we would want to make a nice, pretty circuit like this where all the components are cut nice and short.
So pretty. If
we were doing that in class and getting graded. Okay, so we got a light. Now we need our light sensor. So that's going to be the phototransistor. So we're going to go +5 volts to the phototransistor.
So this is the sensor that sees the light bouncing off your finger.
Right.
And you're going to build it right next to the light.
And then the junction, or the node between the phototransistor and the resistor, is going to be a voltage. And that's going to show us how much light is hitting the sensor, which should show us our heartbeat. And I'm just going to cheat and go back to my previous circuit. I used a 10K resistor. And we could play with what happens when you change this resistor. This is like the sensitivity. So as that resistor gets bigger, the signal gets bigger. But it doesn't need to be very big. So a 10K is brown, black, orange. So I'm going through my resistor pile. Looking for brown, black, orange. And then I'm putting the phototransistor to the resistor to ground.
Lovely.
And then I need another red wire to connect the short side of the phototransistor to 5 volts.
So Jalev says, I'm used to learning circuits as one full circuit. I'm not sure. Yeah, let us know. We're curious. Like we're trying this new method of teaching where we teach piece by piece and draw the block diagram, draw the circuit diagram, build the circuit, and then go back. And yeah, let us know what you honestly think of that method. It might be a little bit more suited for people just getting into electronics than people who are already experienced.
Yeah.
But in any case, you're going to come away with the full circuit diagram at the end of this. Like we will send you a screenshot or you can take one. Like we will get it to you as a thank you for coming tonight.
Okay, so now I'm putting the screen wire from the node where the phototransistor touches the resistor, and we have channel 2 is turned on the NLab. So I'm going to plug this into the row for channel 2. And now we can see a voltage on the yellow line that represents how much light is hitting the phototransistor. That light turns into current. The current through the resistor turns into voltage. So if I were to cover it with my hand, it would go down, but there's enough light somehow sneaking through my hand that the voltage didn't go to 0.
That didn't do anything.
But the whole idea was that red light is bouncing off my palm and hitting that. So if I block that and do this, like we get different amounts. But if I point it towards my studio light and I point it towards the ground, and we see it change. And then the idea is if I touch them both at the same time, so I put them next to each other for that purpose. Now that signal is the light bouncing off my finger, and you could kind of see it changing by a couple of pixels once per second.
So subtly.
It's very subtle, but that's the heartbeat. And this is now where it becomes an electrical engineering problem. I want that signal to be like a couple of volts. Yeah. I don't want it to change by a couple of pixels. In this case, the couple of pixels is probably a couple of millivolts. I want it to be a nice big signal. So we're going to design the rest of the circuit to remove the part of the signal we don't like and keep the part we do like.
Oh, here's a question. How is light being measured like that with an LED only? There is no photoresistor.
So in this case, I've got the phototransistor. That's this component here, which is light sensitive.
Does the phototransistor do the opposite of a photoresistor? I thought we were talking about this the other day.
So a photoresistor would be a resistor, and its resistance changes with the amount of light that hits it. The problem with those is that they don't change very quickly.
Oh, okay.
So even the heartbeat, which is like roughly once per second, might be too fast. Whereas a photo diode
or phototransistor,
we're going to use a phototransistor. There's 3 ways to measure light. A phototransistor changes very rapidly, but the signal is really small, which is also kind of a pain. So the phototransistor is somewhere in the middle. It changes at a pretty medium rate, so definitely fast enough to see our heart rate. It's a nice big signal, so we don't have to use too much amplification. It just has that weird transistor word in it, and we could talk about transistors, but it works like a transistor, so a little bit of light hits it. When the light hits it, it drags current through it. So you could think of it as like a switch. When light hits it, it activates the switch. That's why we needed this resistor, because the current goes through that resistor to ground, becoming a voltage using Ohm's law, and then we're measuring that voltage.
That's right. That's what we're plugged into right now.
And that's what we're plugged in right now.
Oh my gosh, I've been here for 20 minutes already. Okay, we gotta move along.
Okay, so now what we ended up with was not this signal. We ended up with this signal, where it's very flat, and we got a little tiny bump with heartbeats. So what we want to do is we want to take this part of the signal, that constant, and we want to subtract it.
Yes.
And then we want to take this part of the signal, the tiny part that changed, and we want to multiply it. So we'll need...
Can you just write subtract. And multiply? Yes.
And multiply. Sorry, it's been a while.
You got it.
Okay. And what's weird about the subtraction is that amount, it looks like 2 volts, but it's not always going to be 2 volts. So I'm not going to use a standard subtraction circuit. We're going to instead think of this as frequencies. This is a constant, and this is something that changed once per second. So I'm interested in removing anything from the circuit that happens less than once per second. So we're going to use a filter to remove that.
And what that so-called noise represents is the overhead light, right?
The overhead light, which is constant, plus the light that bounces off my finger that doesn't change with heartbeat.
That's right. As in like your finger just moving, because we're always moving, right?
Well, this is the constant, like just the fact that my skin always reflects light.
Oh, yeah. I see what you're saying.
Yeah.
Okay.
And now if I moved less than once per second, it would also remove that.
Got it.
But I don't want to remove more than once per second because that's the information I care about. That's my heartbeat.
Does it also compensate for you kind of moving your finger a little bit?
A little bit.
Because we are always moving.
Really
even
slow
when we're
motion.
even when we're standing still,
Yeah,
we're moving.
Yeah. So that will help with that. And then we need this multiply. So the sensor is going to go to a filter. So that'll eventually be here. That's the filter. And then from the filter, it's going to go to the multiply, which we call an amplifier. But we're not going to go from sensor straight to filter because the filter is going to be made of a resistor, and it's a little dangerous for a sensor's resistor to touch a filter's resistor.
And why is that?
Because when resistors touch each other like that, the second resistor might steal the power from the first resistor, and that might steal all of the signal that we're interested in. So we want to protect the sensor's signal from the filter.
Because if any power gets stolen from this guy, then it can't see your heartbeat.
Exactly.
Yeah.
So we're going to use a circuit called a buffer in between them as a protector. And this might not be like really necessary, but I think it helps.
Absolutely. We get a quick question. We want to use a filter to get rid of the little bumps in the signal.
No, we want to keep the bumps. We want to remove this big constant. The constant is not the heartbeat. The little bump was the heartbeat. That's what I want to see.
Does that make sense? Let us know if you have follow-up questions. Back to our circuit diagram.
So first we're going to add a buffer. And the buffer is from a chip called an operational amplifier. And it doesn't use any resistors or capacitors or anything. It has two inputs, the non-inverting and inverting input, and one output. And then it has two power pins. I'm going to power it with plus 5 volts and minus 5 volts. A lot of times we leave those out because the chip doesn't work without them, so you can pretend they're not even there. And the op-amp I'm going to use is the TL-V272 chip, which is a general purpose bipolar op-amp. Bipolar means that it can use plus and minus 5 volts. And so here's that integrated circuit chip. This particular chip has 2 op-amps on it, which is going to be nice. And it's got a little dot in the top left corner, which indicates where pin 1 is. So there's pin 1 on the top left. And I've used this chip so many times that I've memorized that the top right pin is the positive power and the bottom left pin is the negative power. So we're going to add its power. Red wire for plus 5 volts. I'm going to use a blue wire for minus 5 volts. And that will power up the chip because it doesn't work without power. Making lots of little wires. 1.
I think this guy's name is Mr. Doggy. Am I pronouncing that right, Mr. Doggy? It's funny because we call our dog Mr. Dog.
All dogs are Mr. Dog. Boy dogs and girl dogs.
We had a girl dog, and she was also Mr. Dog.
I bend this wire into the little U shape. Like that guy in there. Okay, so now the op-amp is power. It's ready for us to use it. And take another green wire and go down to the op-amp on the bottom right. It's probably really fascinating watching someone.
Oh my God, it's
wires.
Peter. It's Peter from TikTok.
No way.
Yes, Mr. Doggy is Peter. Peter. Great to see you, man. Thanks for coming. Did you think we died? We kind of we kind of were offline for a while. We were figuring out what we were doing, but
Yeah.
now we're going to be streaming on YouTube 4 times a week, and we're really excited about it.
Okay, so this green wire is this wire. This little green wire is this wire. And so now I should look at that point on the NLab to just verify that the input and the output should be exactly equal to each other. That's the point of the buffer, is it's just copying this voltage here, but is now safe to use for other circuits. So I'm gonna look another wire. And Angie, if you could go into the NLab app and turn on channel 1, maybe.
Yes, sir. Nothing's going to happen yet because you're not plugged into it, right?
Right. Okay, channel 1.
Yeah, 4 times a week, guys. If you want to know our schedule, tomorrow is beginner builds. If you know nothing about electronics, that's where we introduce you to some simple concepts. Wednesday is Resistor Wednesday. That's a private live stream for those who've already placed a $1 reservation. We'll be sending out the link exclusively to them, but we do all sorts of fun things on Wednesdays. We do, you vote on the product features. We give away a kit to someone who is attending the live stream. And Thursday is Sips and Circuits. Tell them about that.
Yeah, I'm excited for Thursday. That's a day where we will take a little bit more chill.
It's our happy hour.
Answer question circuits and maybe build some small things, but mostly just hang out and answer questions.
And sip a choice beverage.
And yeah, the nice beverage part.
We're going to be sipping a different beverage each week, and you're welcome to join us with or without a beverage of your choice. Cool.
Okay, so channel 1 is currently at the phototransistor output. Channel 2 is the output of the buffer. And we can see they're not the same. They're not the same because I had cheated. I had zoomed in on channel 2. So channel 2 right now is more sensitive than channel 1 in software. That's why they are not on top of each other. But Angie, if you want to go back into the settings of the NLab and change channel 1 to be on whatever, 200 millivolts or whatever, match. Yeah. The other way. Yeah, there you go.
Yeah, around there.
Okay, so now they're right on top of each other because they are the same signal. They're buffered and non-buffered at the same sensitivity. So now I'm going to ditch channel 1 because now that we know that, we're going to take off channel 2. I know that the buffer is working. We don't need to see that anymore. So now we're just going to be looking at the output of the light sensor that has been buffered. And we want to do our filter. So we've now got the buffer. Let's move on to the filter. And the type of filter we're going to use is a high-pass filter. And a high-pass filter is going to use one capacitor and one resistor. So we're going to go capacitor, resistor, ground. And then we're going to look at this point in the circuit. And that should now be the exact same signal minus the constant. And so this is like the first maybe magical part of the circuit where it's like, how does a capacitor like do this? We'll have a whole video on that, but this configuration of resistor capacitor is designed to remove low frequencies. And I'm going to use a 1 microfarad capacitor and a 100 kilo ohm resistor. And the frequency that it's removing is 1 over 2 pi RC. Some fun math, where R is 100,000 and C is 1 microfarad. And so that frequency should end up being around 1.5 hertz.
And let's just remind them what it represents. So basically, this is what we're seeing right now on our screen when we do the heartbeat monitor, which is this line. And these little circles here are the heartbeat. And it's way too small, first of all, so we want to amplify that. Mm. And then also, we want to filter out all of this.
Yeah.
And so let them know what that represents.
So that little pulse, we want to make nice and big. So we want to multiply it by like 100, but we can't multiply this by 100 because the constant would be 100 times bigger. It would be too big, it would fall off the screen. So first we need to subtract off the constant before we can multiply by 100. And we're subtracting by using a high pass filter rather than a standard like differential or subtraction circuit. Because we don't know what that voltage is, and it might change every time I change rooms and things like that. So we're subtracting low frequencies, which will remove the constant. Okay, so I need a capacitor and 100K. 100K is brown, black, yellow. Go back into our big mess of resistors. Here is brown, black, yellow. And then there's our baggie of capacitors.
Oh, we got a question. Why is the constant even a thing?
That's the light that's bouncing off our finger.
Always, right?
Always.
Yeah. In order for us to even see our fingers, there has to be light bouncing off of it.
Right. Might also be the light that's going through our skin and hitting the bone or the tissue and bouncing off. And that's a signal that doesn't change, but it's still bouncing off. Okay, and then capacitors have numbers written on them instead of colors. And so this one says 105Z, 105 being 10 times 10 to the 5 times 10 to the minus 12 ends up being 10 to the minus 6 or 1 microfarad. Okay, and so from the output of the buffer to the resistor to ground, and the node where the resistor touches the capacitor, let's put that on channel 2. And my green wire that I used to use is too short now, so we'll make a new one and use yellow. Okay, so now what we're expecting is the same voltage without the constant. And so we'll look at it first and we'll draw it. So immediately right now, we just look at the signal without my finger on it. Green is how much light is hitting the phototransistor. It's almost 2 volts. Yellow is 0 because yellow is green minus the constant. So now if I cover the light from the room, the light that's hitting the phototransistor now is the light bouncing off my palm, but yellow is still 0 because the amount of light coming off my hand is constant. So yellow is 0. But if I move, I can see the same change happen on each. Okay, so if I put my finger there and stay really still.
There's a little something going on.
There's a little something, and you can see it on both green and yellow.
It's still not nearly big enough.
Because we haven't amplified.
Exactly.
So now we need to amplify. But we're not going to amplify green, we'll amplify yellow. Because now that it's centered about 0, when we amplify, it'll stay centered about 0.
So you guys see that we have successfully subtracted all of this and moved this line down here.
Right. Yeah.
So that's what that is.
Right. So now we want the amplifier. And I'm going to cheat and I go that way.
Good.
About that way.
Good idea.
Okay, and so I'm going to use a standard non-inverting amplifier configuration for an op amp. And if we call this one R2 and this one R1, the gain is going to be equal to R2 plus R1 over R1. And I'm going to guess that we want a gain of like 100 or something. Let's see what we did before.
What does a gain represent?
So how much bigger is the signal going to get?
As in like the peak?
Well, right now the peak is like 1 millivolt, and we would like it to be, 3 volts.
Yeah.
So I probably want a gain of like 300.
Sure.
So I'll set R2 to 330K and R1 to 1K. So the gain is going to be about 330 or 331. And so now the signal should be much, much bigger. We won't have to zoom in at all. Okay, so I need a 1K resistor and a 330 ohm resistor, 330K. That's orange, orange, yellow. There's orange, orange, yellow. And I need a 1K. That's my brown, black, red. There. And actually, what's interesting about the circuit as we're building is not seeing any like high frequency noise yet. So usually what you think of as noise would be like a big smothering signal on top of our signal will be all fuzzy. But the signal is so small so far, maybe we haven't seen it yet. So this is where we'll start to see high frequency noise.
And where would that come from?
So in this case, it's probably the fact that the LED lighting in this room is blinking. It's flickering.
Sure. At a rate that we can't really see.
That we can't see, but the light sensor will see. Okay, so I'm going to use this green wire to take the voltage from the high pass filter and stick it into the amplifier. And then, so now we're looking channel 1, channel 2. We'll put this on channel 3. Pick a new color for that. Purple.
We have a visitor from India.
Oh.
I said, oh my, it must be late over there.
Or very early.
We got a good question. When I place a $1 reservation, is it mandatory to buy the kit? No.
No.
You can totally get a refund if you want.
Right.
Absolutely.
But the $1 reservation gets you
20%
off, which is $40 off. So we thought that was a pretty good deal.
Indeed. That is the lowest possible price we can offer the kit for.
Yeah. Okay, so now do you want to turn on channel 3?
Wow, it's almost 4 a.m. for this person. Stayed up to watch this live. That's amazing.
Aw.
Thank you for doing that. Oh yeah, and it's 7 a.m. in India. Wow, thank you guys. Awesome.
Okay, turn on channel 3.
Yes, sir.
So now we're going to see the signal that has been high pass filtered and amplified. And so now we can see
Whoa!
it's fuzzy.
So fuzzy.
And we're not zooming in like we zoomed in on the other channels. So that's raw. And if I put my finger and stay really still,
that's certainly a heartbeat.
it's a heartbeat.
It's very fuzzy.
It's fuzzy. So zoom in time, if you will. Go to like 1 millisecond.
Mm-hmm.
Okay, so
well, now I can't even tell that's a heartbeat anymore.
Right. But we see that the noise is very high frequency.
Mhm.
That's good for us. If it was close to the heartbeat, it would be harder to remove.
Sure.
But it looks like it's in the kilohertz level or above that. So that's good. Go to 10 milliseconds. Okay, there we see some other kind of sine wavy triangle-ish wave. That might be closer related to the lights in the room flickering. But overall, this is not so bad. If you're in a place with fluorescent lighting, that's a big signal that's hard to remove. But this isn't so bad. Okay, so that means we are pretty free to choose whatever next stage of the circuit we want. We're going to use a low pass filter. So now when we look at our signal, what we're seeing is the heartbeat, and it's nice and big, but it's fuzzy.
Is that necessary?
Yeah. So we want to remove that fuzz. And so we're going to use another filter to remove that.
No fuzz filter.
And so this filter was a high pass filter. Its goal was to remove the mean, to subtract the constant. This filter is going to be to remove the fuzz. If you want to think of it like that, remove the high frequency noise.
Great.
Okay, so we're going to take this, and a low pass filter is the opposite of the high pass. It's a resistor, capacitor, ground, and it has the exact same equation. And in this case, I'm going to be really heavy-handed. I'm going to overfilter. I'm going to use the exact same resistor capacitor combo. We're going to make this really smooth. I'll pull out another 1 microfarad and another 100K.
We ship worldwide, guys. Or at least we will when we launch the Kickstarter.
When we launch the Kickstarter and when we figure out how to ship.
Mm-hmm. We know how to ship.
Yeah, we know how. Theoretically, we know how to ship.
Peter is saying you guys should try turning on and off the light to see if it would affect it much. We can do that.
The red LED light or like
oh yeah, good
light?
question. Do you mean our overhead light or
We should do both.
Yeah, let's try it.
Actually, the overhead light is off. Only our studio lights.
Oh yeah.
Okay. Low pass filter, and we'll put this on channel 4. And this is the nice thing about a 4-channel scope. You can see a lot of things simultaneously. And what would be interesting is like sometimes, like for instance, we put that buffer in for protection. If you forgot that, you would have seen probably that as soon as you plugged in the filter to the sensor signal wouldn't be as big as it used to be, indicating that you should use the buffer. If you don't have a scope that has a lot of channels, it's hard to see that kind of stuff.
So many filters. When's the NLab shipping? I'm dying to get my hands on them. Oh my goodness, that's wonderful. We start shipping. So we launched the Kickstarter in April. It ends in May. So May, June is when we're shipping out the first units.
Yeah. Okay, so now the blue signal is before the filter, the red signal is after the filter. So you can kind of see that the red one is smoothing out the blue one.
Mhm.
And that's the heartbeat. So the green, yellow, blue, and red are all the same signal, just with different filters and amplifiers. And in this case, you can probably turn off channel 3 just because it's so fuzzy and
Sure.
making it hard to see the red channel.
Oh my goodness. We got it, guys. We got a clean signal.
Nice, clean heartbeat. It happens to be all negative, and the pulses happen to go down.
Yeah, this is the 0, right?
That's the 0.
So why is it negative?
That must mean that the reflectance of my finger it's less reflective when my heart beats.
Oh, I thought it meant you were dead.
That too. Yeah, so in this case, we probably don't really care if it goes up or down. If you did, you would then add a circuit to invert it. You'd use an inverting amplifier, and you could make it bigger or smaller, but you could make the sign the other way.
Peter's asking, can you flip it?
We can flip it. How about we can do that really fast. So I've run out of op amps. I need an op amp to do that. You just hold on while I make a couple things. So if you've taken an electronics class before, usually these op amp circuits are highly theoretical. This op amp circuit does this, and this op amp circuit does this. So this is a good opportunity to be like, well, what does it mean when the gain is negative? That means that the input is going to be times a negative number. So right now we have a negative signal times a negative number become a positive signal. And the size is already the right size, so I'm going to make it a gain of -1. So we get the same size on the output.
Peter, what did you mean by can you flip it?
Well, hopefully it means make it all positive. That's what we're doing.
Okay. I think that's exactly what he means. Please confirm. Sorry, I meant can you flip the signal? Yeah, I think that's what he meant, right?
Yeah. Okay, and I'm being lazy, not drawing the circuit diagram, but I'll draw it in a second.
Well, Wizzo Jawlab is going to be very mad at you.
Yes, he should be. That's one of the rules in my office hours. No consultation without a circuit diagram. Because you get too many students who come in and say, like, what's wrong with it? I'm like, I have no idea. You have to show me what you meant. So this guy is going to go here.
Wizzo. I will do that, Wizzo. Thank you. What is the website and price of the NLab? GetNLab.com.
Okay, so I'm going to use 2 equal resistors. I chose 1K. As long as they're equal, this will work. And Andrew, if you could set channel 1 back to 1 volt per div, we don't need to zoom in. So I'm gonna plug this into channel. Of course, it's
1 volt.
short.
1 volt per div. There you go. This is not what I want. I want that. 100 milliseconds.
500 is good.
500. Okay.
Because the heartbeat's like once.
Oh yeah, you're right.
We could play around with that if you want. If you zoom in too much, then you can't see the heartbeat. Okay, so now what we expect is channel 1 and channel 4 are equal and opposite.
Oh, that's a good question. I was going to ask if you could create your own simple circuit that reads signals, but I think that throws off the idea of NLab.
Sorry, well,
that is the idea of what we want to do, which is to create custom circuits.
Yeah, once
from
you've
scratch.
built this on your NLab, maybe the next step is to build it with on an Arduino or a Raspberry Pi, and then you would use your NLab to confirm that all these signals are doing what you expect.
Exactly.
For instance, right now it's not doing what I expect, so I must have nudged something. This is what
Tisk.
happens when you don't.
Wait,
cut
maybe
your
you can
wires.
show how the NLab troubleshoots.
So channel 1 and channel 4 are supposed to be equal and opposite. Channel 2 is after the sensor. Channel 2 is down here, is after the high pass filter. So it's still working up to the high pass filter, but channel 3, the output of the amplifier, is not showing me that noisy heartbeat anymore. And then, of course, channel 4 and channel 1 aren't showing me what I expect. So something about my amplifier fell apart. So either the wire that brings it in or a resistor is touching another resistor that shouldn't, or the power fell out.
All the Wizzo says all of a sudden the signals are on the same. That.
Yeah, that's what I'm trying to figure out. So this would be the danger of building your circuit so the wires are long instead of nice and flush, is that they can bend,
they can touch each other. Yeah.
Or potentially fall out or something funny like that. So I'm just inspecting, trying to figure out where that happened.
I'm not immediately seeing. Wait, right there.
Those touch.
No.
Okay, channel 1 is still working. That's good to know.
Yeah, walk them through your troubleshooting process.
So I'm taking this wire, which is connected to channel 1, and I'm now poking around to see, okay, so here's the signal after the high-pass filter, which is also on a different channel. So we can see that those are on top of each other. And then that signal immediately goes over to here. So that would be figuring out maybe this green wire fell out. So channel 2 is in yellow and channel 3 is still good. So then the amplifier. Oh, that's still working. That's plugged into channel 4. Channel 4 is red.
You know, I think you should build the whole thing all over again.
Start from scratch. That doesn't sound very appealing.
No.
Channel 3 is off. That's why I'm seeing it. Channel 4 is after the.
Do you want me to turn it on?
Yeah, that's good. Okay, so the question is, why did channel 4 go away? Oh, and I didn't use a buffer. So now I take out my purple wire, and we'll see that channel 4 comes back. Okay, so I lied. When I said these 1K resistors don't matter, they have to be equal, but they also should be a lot bigger than this resistor, or I should put a buffer in between them. So we will scratch that, and we'll go to 1,000,000 ohms.
Ooh, okay.
So that this resistor is much bigger than that resistor. So it's going to steal some of the power, but not.
See, guys, even the pros make mistakes. He does this every day. Not make mistakes. No. But that's what I like about the NLab. You literally used it to figure out what was going on. You were poking around with channel 1.
Right. Yep.
Wizzo wants to know, what is a buffer? In simple terms, a buffer protects a component from drawing too much power or releasing too much power.
Drawing too much power.
Mm-hmm.
We could look at our circuit diagram in a moment. Okay, now we're back together with 1,000,000 ohms.
But it protects one component from releasing too much power to another component. Right.
Right. So, for instance, here's our light sensor, and we wanted to send the voltage across this resistor to the high-pass filter. But that means that current would go this way, And if this resistor was smaller than this resistor, in this case it's not, so maybe we didn't need the buffer. But if this were smaller because of the frequency that we chose and the frequency set the resistor, then the current that comes out of the light sensor would split. Some would go this way, and then some would go this way, which means that our signal here would get smaller, and that's not what we wanted. We wanted a nice big signal. So this op-amp chip says, I will take that voltage and I will copy it right here. But the current that goes this way is going to come from the power supply. It's not going to come from the sensor. It's just observing the voltage from the sensor and copying it, and it's an active chip. So it's an amplifier, but the amplification factor is 1. So it's not actually making it bigger or smaller or anything. It's just copying it. And in doing so, it's protected this guy so that all the current from the light sensor goes through the resistor, making a nice big voltage here, copy that voltage here, and then we use that voltage, and then the op-amp is capable of sending a lot of current this way, so we're not worried about this resistor being too small.
Well, he wrote, isn't a buffer just a resistor? That's a fair question.
In this case, the buffer is an operational amplifier configuration we call a buffer. I think there are other ways you would use a resistor as a buffer, but in this case, we're using the operational amplifier as a buffer.
Yeah, I guess like I kind of understand what he means, which is that a resistor is kind of a protective element as well. So like what sets it apart?
So I guess if the resistor is very big, it would prevent too much current from flowing.
Mm-hmm.
In this case, our fear is that the resistor we picked here was too small, in which case it draws like potentially a lot of current.
Mm-hmm.
And if the thing that is supplying the current can't supply that much current, then the signal would get squished.
Great.
Okay, so turn off channel 3 and let's look at channel 4 and channel 1, I guess. And so channel 4 in red, well, that was our original signal that went negative. And channel 1 in green, that's the negative version of it.
That's so pretty.
But you could, so they're kind of mirror images. Green became more fuzzy for some reason. And that's probably because these resistors are big and the op-amp would prefer if the resistors were small. So it's still operating the right way, but it's added some noise. And so if we wanted to get rid of that noise, we would add another low pass filter. In this case, we just keep it like that. Okay, so now we could take that signal, we could apply it to an LED, and we could make that LED blink. There's a couple different circuits that could do that, but I don't know if we've kind of run out of time, so we could just keep it here.
Yeah, I think that's good enough. Unless, well, let's ask Wizzo, who has the strongest opinions.
Here's what I did on the other circuit, the red and green one. We took the output of our filter and sneak this up here to our LED amplifier. And so if the signal is big enough, we can just apply it to an LED directly. In this case, I'm going to build a special circuit with an op-amp to make the LED nice and bright. And so this is, think of this as like a regulator circuit. Oh, it got a little too big. Okay, I think we just made it. And the red-green LED is one LED, one physical package of LED, but there's two LEDs in it, a red and a green, and they face in the opposite direction. So when this voltage is a positive voltage, current will go this way and the red will turn on. And when this voltage is a negative voltage, current will actually leave ground and go towards the negative voltage, turning the green on. And then the size of the resistor is just going to sit how bright it is. Maybe we'll use a 1K at first, and we could play with that. So that's a special LED. It's 5 millimeters in this case. It's opaque. It's not clear. So it looks like the super bright red, but it's not clear. And in this case, it doesn't really matter which way I plug it in. It's got a long and a short side, but one side's red and one side's green. And so I'm just going to stick it in there. And then find my another 1K resistor. And it's turning on because there's no input to the op-amp yet. It's just random. And then we'll take our signal from the op-amp, stick it to the input of this op-amp. Okay, now
Ta-da.
In
There's your heartbeat, and it turns green.
this case, it might be going light red and dark red, or bright red and dim red, because the signal isn't flipping positive and negative. So it kind of looks like a candle flicker, but each time it gets very bright, that's a heartbeat.
Yay. Wow, right on the dot, 9 o'clock. They doubted us. They're like, the stream's going to go overtime. You always do this. You always end right on time. Wizzo, is that helpful for you? This is the full circuit diagram.
And I think this part probably wasn't necessary, but it was a fun little add-on.
In the circuit, do we connect the end of the resistor to the phototransistor?
So way back up here, phototransistor, resistor, ground. And where the phototransistor touches the resistor is also a wire that goes to the op-amp. So yes, the phototransistor touches the resistor.
Oh, he says before that.
The phototransistor is connected to power. So the phototransistor is not like a solar panel. It's not like a photodiode. A photodiode, when light hits it, it makes voltage and current. It's like magic. The phototransistor is more like a button. When light hits it, it closes the switch, allowing some current from 5 volts to flow through the phototransistor, which then flows through the resistor, making a voltage here that we're then seeing.
Yeah, Mr. Doggy, Peter just said we have to collaborate with Hack Club, a nonprofit that helps teenagers do coding. Absolutely.
Yeah. So the next fun part of this would be, now that we have that signal, we could read that into your computer into Python, and then we can digitize it, and then we can count the pulses. But that's not trivial. That's, you're looking at this voltage, it's changing with time, and you're being like, well, when is it the big point?
So he's asking, so we have 2 circuits here, one that sends light and the other that catches light.
That's right. But they're kind of like physically 2 circuits. One light here, one's a pretty simple circuit here. There's just always outputting light. That's the red light. And then all the rest of this is the sensor.
Yeah. It's almost like 2 sections. It's like the one that sends light, the one that catches light, and then all the corrections.
And so in your smartwatch, there's essentially 2 sets of these, a green and an infrared, and then 2 sensors. And potentially it could be 1 sensor if it's sensitive to both colors of light. But what they'll do is they'll turn on one and then turn it off, turn on the other and turn it off. And when this is on, they'll read here. And then when the next one's on, they'll read here. And then they'll compare the 2 signals to see your blood oxygenation level. So that's a pulse oximeter.
Crazy.
And then what they can also do is that when they turn off this and they read this voltage, they'll see what signal are they getting from the ambient light. And then they could figure out what kind of noise profile there is. And then they could do their filters in code instead of with resistors and capacitors, or they could just do more filtering in code. So it can get way more complicated than this, of course. But yeah, the ability to turn this on and off gives you a lot more interesting stuff to do.
Guys, thanks so much for attending. We hope that was helpful and fun. Should we switch screens, or Wizzo, do you have everything you need? Oh, an important question. You guys showed a circuit with multiple LEDs where they all connected in serial and they had a fading light effect. Do we have that here?
That was in one of our shorts. Was that red, green, and blue, or was in one LED, or that?
Was he talking about the heart that kind of like fades in and out?
The heart. Yeah, that was just put more LEDs here, and they'll all do the same thing.
In series, right?
In parallel.
Oh, in parallel.
Right. In series, it becomes difficult because you need a bigger voltage, because every LED needs another 2 volts.
Sense.
When they're in parallel, that means that more current comes out of the op-amp. So as long as you don't put too many in there, the op-amp will be able to power all of them.
Oh, that's wonderful, Peter. The organization paid for him doing the first project of making a circuit and shipping, and supplied all the materials and paid for everything.
Oh, wow.
That's awesome. Great. And one more question from Wizzo. All the amps here are TLV 272.
That's right. And I'm using those because they work nicely with plus and minus 5 volts. If you were going to build this circuit again with just a positive power, you wouldn't necessarily need this. This is maybe 50 cents more expensive than maybe the MCP 6002 if you wanted to do all positive. I think it's 6002. And so then you would use plus 5 in ground or plus 3.3 in ground. Circuit would get a little bit more complicated because now that you don't have negative circuits, all of these grounds, this ground and this ground need to be half of your power supply. So that could be another thing that we do. So if you have plus and minus 5 volts or plus minus 9 or whatever from batteries, this would all work fine. I don't know what the maximum voltage here, but this one would be when you're working with an Arduino and you wanted to save 50 cents.
Cool. Any other questions before we drop off? Shall we switch to our faces, or will people get mad? Let's find out. Here we are. People are like, no. Let's see. Okay. I don't see any more questions. Yeah, Wizzo, do you have any other questions? Like you said, I think I get it. Anything else we can clear up for you? Oh, he just goes, oh,
get it now.
I didn't catch that. Fantastic. I think this is delayed a little. Is that?
Oh, probably.
Is that possible?
Yeah, it's
yeah. Anyway,
great.
Guys, thank you so much for coming. We're really thrilled with the turnout. We really weren't expecting anybody. So if you liked this, please tell your friends. We're gonna stream Monday through Thursday from 8 to 9 p.m. Central indefinitely. And if you can't make it live, like if it's 4 a.m. where you are, feel free to watch the recording. We post these. But yeah, we would appreciate if you would just spread the word and spread the love, because our Kickstarter is launching soon. And yeah, we really need the support. So thank you all for coming.
Yeah, thanks.
Bye.